Welcome back everyone, my name is Dustin, and this is going to be the start of our physics journey for Scion2D. The physics library that we're going to be using for Scion2D is Box2D. Box2D is a battle-tested physics simulations library, and it's perfect for what we need. So the goal for this video is to go over a small presentation of Box2D and how we're going to be using it, download the Box2D library, and then start the Scion physics project and add that into our game engine. Now, if you want to learn how to create your own physics engine, or at least dig deeper into it, in one of my last videos, I talked about the Pakuma Online School. It's a great school. They have their physics course. And this is the course right here from Pakuma. It's a 2D game physics. It's done really well. Gustavo goes over all the principles and you get to create your own little physics engine. I highly recommend you check it out. I did this course and it's definitely worth it. However, for our game engine, we're not going to be using this. We're going to be using Box2D. So now that we got the intro out of the way, let's get into the presentation. Alright, so now we're getting into physics with Box2D. So in this little presentation, we're going to go over some of the functionality of Box2D. However, a little disclaimer at first, there's way too much stuff to go over to be able to do it all in one video. So we'll be doing a bunch of different videos covering different aspects of Box2D. Physics itself is a humongous subject to cover. So even if I do get into the depths, we're not going to get that deep. So you're going to have to be able to do some research on your own. Okay, so let's get started. So what is Box2D? Box2D is a 2D rigid body simulation library built for games. Box2D allows us to make our object move in realistic ways and to make our game world more interactive. Box2D will handle most of the physics concepts that we will need to use in our game, such as mass, force, friction, torque, and various impulses. Box2D is also easy to use and set up. So that's great for us, because that's what we need right now. Okay, let's go over the world. In every Box2D program, there has to be the world. The world controls all of the physics simulations that need to take place in the game, such as different forces and collisions. The world also manages all the memory and the objects that use physics in the game. So if we delete an object, we have to ensure that any user references that we have are also removed, because it will actually delete the underlying pointer or data for that particular body. You can also perform raycast and ABB queries. We'll definitely be getting into raycasting in a later video because we will be using it. Alright, let's go over how to create the world. So creating the world is pretty straightforward. All we need to do is use the B2 world object. The B2 world constructor takes in a B2 vec2 for the desired gravity of the world, so we can just create a gravity vector and pass it into the new world object, as you see here. This way works. However, we don't want to do it this way because then the world will be created on the stack. And once it goes out of scope, the whole world will be destroyed and the bodies that go along with it. So what we'll do is create a shared pointer of the world and add it to the registry context as you see below. If you see here, we just create a simple alias for the physics world, which is equal to a shared pointer of the B2 world. And then we create a new physics world and we send in the gravity vector. You see there that B2 vec2 right here. And then what we can do is send it into the registry context like other things that we have done before in our game engine. Now, we might not want to send in the gravity like this. We may want to hold on to it in a variable of some sort so it's easier to change and so we know what the gravity is without having to query the world to get what the gravity is. Alright, so after the world is created, all of the physics simulations need to be updated. You do that with the B2 world step. If you take a look at the step function will perform the collision detection, integration, and constraint solutions. And this takes in the time step, which is the amount of time it should take to simulate. And this shouldn't be varying. According to the documentation, this should always stay the same or try to remain the same. Then it also takes in an int32 for the velocity iterations, for the velocity constraint resolver. And then it also takes in an int32 for the position iterations, for the position constraint solver. After you do the step, you can call the clears forces function. This is not necessary because you can set the world to auto clear. Actually, it auto clears by default. However, if you want to do sub-stepping, it's recommended to clear the forces after you do your step. Alright, as we talked before, Box2D is a rigid body physics simulations library. So bodies are one of the most important parts of it. So let's get into what a body is. Also, the world is what controls the body and creates the bodies and holds on to manages the memory of each body. So what is the body? A body in Box2D is a rigid body, where in physics is a solid body that does not deform or change. A body doesn't necessarily represent something you can see. However, it does represent all the things that make an object physical. A body's properties consist of the mass, usually in kilograms per meters, linear and angular velocity, rotation or angle of the body, the positional coordinates in the world, and many more properties once fixtures and body definitions get involved. So let's take a quick look at the Box2D docs to take a quick look at the body class. So this is the body class here. And there's many different functions and stuff that we can use, and we'll be going over a lot of this stuff as we go along. But as you can see here, we have fixtures, and then we can destroy it and create it from here. The position, the transform is just the position and the angle of, it's kind of like our transform component, the same idea. Linear velocity, apply force, apply linear impulse, and we'll be going all over this in later videos. So now that we're looking at fixtures, what is a fixture? Let's get into that. All right, so what are fixtures? The shape of the body and some of the other properties are defined by the body's fixtures. I say fixtures because a body can consist of multiple fixtures. When bodies collide with each other, the fixtures are what determine how the bodies should react to the collision. Fixtures have many properties that we can manipulate, such as the shape of the fixture, the coefficient of friction, the coefficient of restitution. The restitution is the elasticity of the body, or the bounciness, that, if that is a word, of and the lower the restitution, the less it should bounce upon collision. Then we'll have the restitution threshold. Only collisions with a velocity above the set threshold will have restitution applied to them. The density of the object, usually represented in kilograms per meter squared. The more dense an object, the more of an impact it will have on another object that is less dense upon collision. Also, is the fixture a sensor? A sensor is basically just a trigger. It will collect information, however, it will never generate a collision response. It does generate contact information though. We will look more into this when we create the contact listener later on. And then we have filters. We'll go over filters in the next slide. Fixtures can also have user data that is application specific. However, we will go over that in a later video. Now let's take a look at contact filtering. The B2 filter structure contains the following. The U16 category bits. The category bits are used to set the category that you want the body to fall under. We are using a uint16, so we'll have 16 different categories that we could use. You normally only set one bit or place the body in one category. You can define the categories in many different ways, and we'll go over that in a different video. Next would be the mask bit. The mask bits are used to determine what other objects or bodies your body can collide with. Think of it as a bit mask. And what you would do is check mask bits against the category bits of the body that it's colliding with. If the value is not 0, that means the object can collide with each other. If you see this here, and you'll have to check both bodies, both masks, to make sure that they both can collide with each other. Lastly would be the group index. You can place the bodies into collision groups. If the group index is 0, the category and mass bits are what is used to determine collisions. If the group index of the colliding bodies are the same and positive, they will be colliding. If they are the same and negative, they won't collide. And if they're a non-zero value, the group index is what takes priority. The category and mass bits will be ignored. Okay, so that's enough about filters for now. We'll definitely have to be getting into those in more depth later. So now let's quickly go over how to create a body in the world. Alright, the first thing that we need to do to create a body is to define the B2 body def. The body def has a bunch of properties that we can set. These properties are the body type, so it's a B2 body type. And those types are, is it a static body, is it a dynamic body, or is it a kinematic body? And we'll go over those in later videos as well. A vec2 for the position, a vec2 for the linear velocity, a float for the angular velocity, a float for angular damping, the gravity scale. The gravity scale is how much do you want the force of gravity to affect the object. So you can have a higher gravity scale. So 1 would be regular gravity. If it's 5, it'll be 5 times the gravity on that object. And if it's 0, gravity will have 0 effect on how the body moves. Do we want to allow this body to go to sleep? That is more for a performance type thing. If there's nothing touching it or dealing with it, it'll go to sleep. Do we want the body to be awake? Do we want the body to have a fixed rotation? That means it will not rotate. If any angular forces are applied upon the object or the body, it won't rotate. It'll maintain the same angle. The angle won't change. Is it a bullet? Bullets take more processing power because of speed, and we'll go over that in another video as well. Is the body enabled? And there's also user data. And user data is application specific, and we'll also be going over how I use it for Scion2D. I've already have my own way of using the user data. However, when we go over it, if you don't like my way, feel free to change it. That's why it's application specific. Alright, so let's take a look at a simple snippet of creating a new body. So here we just create a basic new body def, and all we're setting is the body type to a dynamic body and its position. That's all we're setting. There's other things that we can set. We can just leave that for now. With the body def created, we can now use the world that we created earlier to create a new body. The create body function returns a pointer to a new body that was created in the world. When we actually do this in the engine, we'll actually be making a smart pointer wrapper to handle the lifetime of the body. So we don't have to worry about deleting it from the world. Once our object, so say we kill an object in the registry, once the component for this dies, it will automatically kill the body for us. We'll basically be doing a wrapper like we did the SDL wrappers for raw pointers that we made earlier. So now that we have the body, we need to create a fixture for it. And we're just going to create a simple box shape for that fixture and set a couple of the fixture's attributes. And once we are done here, we can now use the body to create the fixture with P-body create fixture, and then we have to send in the fixture def as a pointer, or send in the address of the fixture def. The set fixed rotation is optional. I just threw it in there as an example. All right, so that's really it for creating a body. There's so much more that I could go over. However, I believe that it is easier to show through the program for what we can create, and I'll explain more as we go. So let's start the new Scion Physics project and let's get physical. All right, everyone, this is the Box2D GitHub repo on Aaron Cotto, Box2D. Give it a star. To install it, what we're going to be using is VC package. Now, there's other ways to install it, so you can build it for Xcode and different, you can use CMake if you like, but it shows you right here of how to build it using VC package. Now, I've already done this, but I'll show you how we do it, okay? So what you want to do is open up a command line. Any command line will do. Then I just got to go to C. If it'll let me. Okay, then I want to go to, from C, I want to go to VC package. VC package. Did I spell that right? No, VC package. Okay. All right. And if you don't have VC package, I recommend you download it now or do another way to actually build it for you. You can use CMake, but we're going to be using VC package. And then once you're here, so once you have VC package installed, you can just follow this here, or you can do this here. This is what I'm going to be using. It's VC package install Box2D x64 Windows. Now I'm going to hit it. I've already got it installed. Yeah, so it's already saying that it's installed. And what I have here is the 2.4.1, and that is the latest. So if we go to the releases here, right here, 2.4.1. So I already have the latest installed. So if you're using VC package, it should do that for you. So if you're using VC package and you just put it in this here, it'll create a static library for us to use and you can reference it. So you can just go to your VC package folder here. Then there's packages or install here, and then Windows static for me, libraries. And I have Boost here as well. So that's a different one that I have. Here, we go to VC package. Packages. See, I use Boost as well in some of my other programs. So VC package is a really good package manager. I recommend you use it in my opinion. So installed, Windows, binaries. Yeah, you see you have Boost. Also TinyXML, I've used that as well. Box2D, downloaded it all for us. Libs. Box2D lib, see it's here as well. Thrift, some other things that I dabble with. All right, so now that we have Box2D installed, we're gonna wanna create another new project. So we'll come up here, click on our solution, go to add new project. If you've made it this far, you've done this before. So let's go here and we'll call this Scion Physics, and we'll create that. Now that we have Scion Physics created, I'm going to want to make a new folder for it here, and we'll just call this Physics. And we have to go into the properties of the project, and we're going to want to change this to a static library and change our standard to C++20. Now, you could go to the preview for C++23, but we'll stick to that right now. C++20, and I might change that later for us. So that's good for now. Make sure it's on all configurations when you do this so it's easier. Cool, that's already set. And the first thing I'm going to want to create is actually the Box2D wrapper. As a matter of fact, that's all we really want to create for the physics library at the moment that we're making. So new, And we're just going to have a header file here. And we're going to call it Box2D wrappers.h. Cool. Now that we have our Box2D wrappers, let's see if we have our Box2D. Box2D, Box2D.h. And let's include memory. All right, so it's namespace. I'm going to use Scion Physics for this. Feel free to use whatever you like. And right away, I'm going to create that alias for us. So we're going to say using physics world. And that is going to equal to a shared pointer of a B2 world. Cool. Now, if you remember the SDL wrappers that we made, so we could wrap the SDL pointers into smart pointers, we kind of want to do the same thing with the Box2D bodies. So the B2 world holds onto each body as a raw pointer. So we're going to have to make a custom deleter. So we'll call this the body destroyer. So let's say struct body destroyer. And we're just going to have a void operator, and it takes in a B2 body pointer, not B2 bot, B2 body pointer of the body, const, and we'll just make this. Cool. Every body has access to the world that it was created in. So what we do is we call get world, and then we want to destroy the body and send in the body. Cool, that's it. So that's our custom deleter for us. So once we have that, we can create a new function that'll generate the smart pointers for us, and we'll just call that a static std shared pointer of a B2 body. Make shared body, and it will take in a B2 body pointer of the body. And then this is going to return a shared pointer of a B2 body. And it takes in the body and the custom deleter, so the body destroyer. All right, that's it. Now, there's going to be more stuff that we're going to be wrapping later on, but we're not going to worry about that right now. Really, for our physics library to get started, this is all we need. Later on, we're going to need the contact listener, user data, and other things like that. We'll get into that in another video. The next thing we need to do is actually go and then create a physics component. So let's go into our core. Okay, and the first thing I'm going to want to do here is create a reference. So here in our core, we're going to want to go to add reference, and we're going to want our physics, and we'll say okay. And then we're going to want to go into the properties of our core project here and add that in to our VC directories, kind of like we've been doing before. Here, Scion2D, Scion Physics, cool. Solution dir, and we'll just copy this because we're going to go and put it in the editor as well, because we might as well do that now. So in the editor, go to add new reference physics. All right, and then properties, just put it at the bottom. All right, that should be good there. So now, inside of our core, go to our ECS and to our components and add a new component. And this will be the physics component .h. And we're going to include our physics wrappers. And we're going to want to say, what was our namespace for our components? Let's just grab that now. Let's grab this. Go back to our physics component. And let's include sol for wrapping it. GLM. And ENTT. And then put our namespace in. Cool. So right away, I'm going to create a couple const expert values. And it's going to be const expert float meters to pixels. Because everything in Box2D is considered in meters. So we need to know its equivalent to pixels. And you can pick any value you like. The value I've used that I like the best has been 12. And then we need to make another one and to revert it back. So pixels to meters. And that's just equal to 1.f divided by meters to pixels. Cool. And we're also going to make our own little wrapper enum for the rigid body type or the body type. So enum class rigid body type, and it's going to be static, it's equal to 0, kinematic, and dynamic. The ones that we're going to use most often are going to be static and dynamic. And before we create the component, I'm actually going to make something called the struct physics attributes. I find it's easier to create a small struct and then pass that in rather than trying to create a huge constructor. So here we can add in all of the attributes that we want to initialize the physics component. So it's going to have a rigid body. So it'll have its body type, and it'll say E-type. And it will default to a rigid body type static. So it's going to default to a static body. Then we're going to have the density. That'll just default to 1. You can put it to whatever you like. We're going to have the friction. And it's just 0.2 F. Restitution. (0.2 F). We're going to have some more float. It's restitution threshold. Threshold 1.f. We probably don't even need to hold on to that. The radius, just in case we're using a circle. And the gravity scale. And we'll just start that at 1. And then we're also going to have the position, GLM, vec2. Now these are the starting position, 0.f, the scale, 1.f, the box size if it's a box, and that'll just start at 0.f, and the offset. Start that off at 0. Bool be circle. So is it a circle? False. Be box shape. Start that off as true. Most of the stuff will be boxes. Be fixed rotation. True. And then we're also going to have a couple variables for the filter category and the filter mask. uint 16t filter category. And it's going to start at 0. We don't really care about these right now. I'm just putting it in. I always do unit. This should be uint. And the filter mask. That'll also start at 0. Then the int 16t. And this is for the group index. And that's just going to start at 0 as well. We're not going to worry about this stuff right now. We're going to go over this in later videos. But this should be good for now. Okay. So we'll have a class physics component. And then we can say Scion physics world MP physics world. Then we're going to want to have a shared body, shared pointer to a body, so B2 body. And then we'll call it MP rigid body. And then we're going to want to have our physical attributes. So physical attributes, and these will be our initial attributes or attributes. Okay? Because this is what we're going to be starting with. We set in the physical attributes, and then we'll be changing things with the Box2D library. Okay? So then we'll say public and we'll have our physics component constructor, and that will take in the physics world. So Scion physics world, P physics world. And it also take in a const physics attributes. That'll be a reference, and it's physics attributes. Cool. And for now, the destructor can just be default. And we're going to have two functions for now, and it's going to be void init. And the init is going to take in the window width. And it's also going to take in the window height. We're going to need the window width and the window height in order to position our body in the correct place, because the origin of the world will be in the center of our screen. And we also want to be able to get the body, so we can go B2 body pointer, get body. And we're just going to return MP rigid body dot get. Then we're going to have our static void create physics Lua bind, and that'll take in our soul state Lua and the registry. Okay, so let's add these in. Let's go here. Let's quickly take this. So this here is going to be a little to-do. That's going to be our challenge. So challenge, create the beginning, I don't know if that's spelled right, of the Lua bindings. And that's going to be a little challenge for you guys. So create the beginning of the Lua binding. So what I would do is bind the physics attributes. And then bind the component. All right. For our initializing, we're going to do our physics world. And that's going to be P physics world. And our rigid body will just be null pointer for now. We'll create that inside the initialization function. And then our initial attributes will be our physics attributes. Okay. Okay, so the first thing we're going to do in the init function is check to see if the world exists. So if not, MP physics world. So let's include our logger here. So if we don't have the physics world, we want to just say have an error. Scion error. Fail to initialize the physics component. Physics world is null pointer. And we'll just return from here because we're going to need the physics world for this. So the first thing I want to do is check to see if it's a circle. So we just go bool be circle, because if it's a circle, it'll take precedence over a box in this case. Initial attributes be circle. Cool. And then we want to create the body def. And that's b2 body def. And that's body def. Okay. And then we'll just say body def dot type is equal to static cast b2 body type of our own type. And if we quickly go to this here, all it is the same. So our static is 0, kinematic is 1, and dynamic is 2. Okay. So now we're going to want to set the position of the body def, the initial position. Set the initial position of the body. Okay, so what we do is body def dot position dot set. And this is where the width of the screen comes in handy. Okay, so if you look at set, it's two positions, your X and Y position. So the first thing we're going to do is set the position based on the X position. So m initial attributes dot position dot X plus is there an offset? Initial attributes dot offset dot X minus the window width, but we want half the window width because we're starting in the center. The world is in the center. So times 0.5. And then plus, we want to check to see, are we a circle? So be circle. So if we're a circle, I just want to circle. I just want to add the radius, initial attributes dot radius. If not, we want to use the box size dot X. And then we want to multiply this by the scale. Dot X times 0.5 times meters to pixels. So I messed up on a bracket somewhere. Oh yes, sorry. This doesn't need to be here. Cool. All right, hopefully that makes sense there. And we just copy this, paste, get rid of this, change this to Y. That can stay radius because it doesn't change, but box it does, X and Y. Window height. Y and Y. Cool. All right, so now we can set our gravity scale. So body def dot gravity scale is equal to the initial. Now you can always change this stuff later on. Body def dot, is it a fixed rotation? Initially. All right, so now that we got here, we set the position, we created our body def, we can now create our actual rigid body. So create the rigid body. And we can go MP rigid body is equal to Scion physics make shared body. And we're going to take our world, MP world, and create a new body and send in our body def. Cool. And let's just do a quick check to see if the rigid body was created. So if not, Scion error failed to create the rigid body. Just return. Now, if we ever get these errors, this is on the programmer to deal with these. Okay, so now we want to create the shape. Create the shape, B2 polygon shape, and we'll call this the poly shape. B2 circle shape, and we'll just call that the circle shape. And we'll just check to see if it is a circle. So B circle, so we already have that. We can say circle shape dot m radius is equal to the initial radius. And then here, else if m initial attributes dot, is it a box? So if it's a box, we gotta go poly shape dot set as box. And we're gonna want to use the origin of the box needs to be on the center of the box, or center mass. So we need to go pixels to meters times m initial attributes dot box size dot x times the scale times 0.5 for half. And I do the same for y. Cool. And then else if, not even else if, just else. We'll leave this now, but this will be our polygon shape. So we'd have to do a to do, create your polygon shape. So if it's not considered a box, so if it's got more than four sides or less than 4 sides, then we're going to want to do this here, and we'll cover that later. We don't need to worry about that now. Let's get it going. So now we want to create the fixture def. That's B2 fixture def. Fixture def. And here we're going to do the same thing. So if B circle, we're going to want to set the fixture def shape to the address of the circle. Else, we want to set the fixture def shape to the poly shape. Cool, and then we can set a few of our fixture def attributes. So fixture def dot density set the friction, the restitution, and the restitution threshold. And now that we got there, we want to create the body fixture. So, rigid body, create fixture. Now, if you take a look here, it returns a pointer to the fixture. So you can check to see if it actually created it successfully. So we can go auto P fixture and check to see if P fixture was created successfully. Scion error failed to create the rigid body fixture. Well, don't really need to return. but just leave an error there. You can usually put in a cert or something here for new programs or whatever, or stuff that you're debugging. You put a certs in to make sure that it's actually working as expected. Okay, so that's the start of our physics component. I know it was a lot. So now we actually have to start our physics system. So let's go here and go to our systems, and we're going to add new item, header, physics system.h. Awesome. And the physics system is going to be similar to our other system. So we can just go here and just grab this animation system short. Paste that in. And let's change this to the physics system. Physics system. All right. Now we're also going to send in the registry here. So we don't know if the registers, we could use multiple registries. So this registry here might not be the same registry that we want. This might just be the main registry, which will hold on to other things. But so we'll just add this in here so it's being sent in. So registry, reference, registry. So it's sending in a registry to the update function as well. And let's create this here. So we create our physics system. So let's go to our physics system.cpp. And let's change this here. Name space. Grab these systems. It's snowing a lot here outside. Grab all this. Get rid of that. Get rid of this. And our initializer, all we need to do is set up the registry. Cool. And we can do our update function. First thing we're going to need is we're going to need to grab a few components. So let's go include, and let's go ECS components, and we're going to need the box collider component, and we're going to need the circle component. Did we call it circle or circle collider? I don't remember. Circle collider component and the transform component. And the physics component. And we might as well get the logger in here just in case. Okay, so for the update, the first thing we're going to want to do is get the view, and we'll call this one the box view. So auto box view is equal to registry.view. And this one's going to have the physics component. Oh, let's also add this using namespace Scion core ECS. Cool. And try again. Physics component. And then we're going to have the transform component. So that means this view needs to have all of these things. So transform component and physics component. Cool. All right. So now that we got the box view, we need to make something called the scaled width. So that takes the width of our screen, which our screen right now is just 640 by 480. So we're going to have to do a better way to do this. And we'll do that later on. But right now we'll just go auto scaled width is equal to 640.f divided by meters to pixels. And then 480 for scaled height. Let's quickly go to our application so I can show you what I mean. So 640 by 480 is what we're setting it up to at the moment. I might as well change this to physics tests. Okay, so let's go back to our physics system. So 640, 480, now this stuff's all temporary here. We're gonna change how we do that in a later video. So now let's loop through our box entities. So this will give us the auto entity for each of in the box view. Okay, so we're gonna get the physics component, and that's equal to view.get physics component. Sorry, it's box view. And it's for this entity. And then we want to get the rigid body. So auto p rigid body is equal to physics dot get body. And we want to check to see if it's null pointer. So if p rigid body is null pointer, we're just going to continue because we're not going to try to check anything with this because we will end up dereferencing a null pointer and we don't want to do that. So now that we made that check, we can go auto, get the transform, because we're going to actually have to change the transform component based on the physics world rigid body values. Okay, so that's what we're doing here. Box view dot get transform component, and that takes the entity, and we also need the box collider. And change this to box collider. So first thing I'm going to want to do here now is get the body position, the actual rigid body position. So const auto reference body position is equal to p rigid body get position. And then we need to update the transform position based on the body position. Okay, so we'll go transform dot position dot x is equal to scaled width divided by 2.f plus the body position dot x times meters to pixels minus the box collider width times the scale divided by 2.f minus the box collider offset. Cool. That's the x position. And then we want to do it for the y position as well. So just change this all for y, height, y, scaled height, and y. Cool. That should be everything we need there. Oh, yeah, there's one more. If we're not fixed rotation, we're going to want to adjust the rotation as well of the transform. So if not p rigid body dot is fixed rotation, then we're going to go transform dot rotation is equal to GLN in degrees of the p rigid body get angle. All right, now that's perfect for everything that has a physics component. That's funny. It's perfect for everything that has a box collider component. However, we need to do this again for any that have a circle component. So let's put that in there now. Change this, copy this, change this to circle view. Change this, circle view, this to circle collider component, and change everything in here. Circle view, circle view, circle view. Oh, that's not circle view, sorry. Circle view, circle view, circle view, change this to circle. And good. And change this to circle collider. Change this here. Cool. So everything can basically stay the same except for the radius. here, this needs to be radius. And it's no longer divided by 2 here because the radius is already divided by 2. So we don't need to do that here. So we can do that and that. And that should do it for us. So that would be a simplified version of the physics system for us. All we're doing here is basically changing the transform based on the actual Box2D values. Okay, so that's what we're doing here. Okay, so now that we have our physics system and our physics component, let's start adding those into the actual application. Okay, so here in our initialize, we're just going to come down here, anywhere really. Well, we'll just put it at basically the last one. So before all this, let's add in, let's just copy how they do it with the camera. So create the camera. And here we're going to just add that in, and we're going to change this to our physics. So the first thing we're going to need is create the physics world. Create the physics world. And we want to go, well, before we do that, we need to add a few things in. So let's go up to our systems and add in our physics system. Physics system. And the components, might as well add in our physics component here. Box collider. And circle collider. We're going to be removing all this stuff later on, but for now it's good for testing. So we have our physics system, physics component, and let's go back down here. Cool. So we're going to say P physics world. And let's just call that Scion physics world. Make shared B2 world. And we're gonna have to send in gravity. We're not gonna hold on to it right now. We're just gonna send in a B2 vec2. Vec2 of 0.f 9.8f. Cool. And then let's add that to the context. So we'll just change this here to physics world. Send in the physics world. Fail to add the physics world to the registry context. So we don't need this here. So now that we have our physics world, let's create our physics system. So this one we can just say auto p physics system is equal to std make shared Scion for systems physics system, and that's taking in our registry. Then we're going to want to add that to the context. That's a shared pointer of Scion for systems physics system. Takes in the physics system. Why is that unhappy? Oh, silly me. Okay, cool. Then fail to add the physics system to the registry. Cool. All right, so now that we have our physics world and our physics system, let's actually go down here and add in some test stuff in. Okay, so down here, still have our test font. So let's add some test bodies to the registry. Right now, we can't do this in Lua because we don't have any of the bindings yet, but we'll just make those here. So down here, let's just go using namespace Scion for ECS. Then we're going to say auto reg. Let's just get the registry from the registry. Go to MP registry, get registry. And we're going to say, just create an auto entity one. Entity one is equal to reg dot create. Then we could say auto reference transform one is equal to reg dot in place. Scion for ECS, we don't have to do that. Transform component, and we'll create our transform component that takes in an entity one. Then transform component. And let's just start this at position is equal to glm vec2, and let's just say 320.f and 0.f. And we're just going to start the scale at 1. So there's our transform. And let's make a circle component for this one. So auto circle comp. Let's just say circle 1. And we gave that a reference. Circle 1 is equal to registry dot in place circle component. Takes in entity 1. And our circle component. And that's just going to have a radius of 64. Because I forgot to say I have a little soccer ball that we need to add here. So let's go to our asset manager dot add texture. And that's going to be a soccer ball. And that's going to be in our assets, textures, soccer ball.png. I don't have that there, but I'm going to put that there right now. And we might as well get that texture now. So auto p texture equal to asset manager get texture soccer ball. Cool. And that soccer ball is just this little soccer ball that I got off of Open Game Art. So we're going to put that into our folder now. So in the editor assets, textures, I'm just going to paste in this soccer ball. Cool, and I've got it. And now that I have my circle component, I want to create my actual physics component. So let's go auto reference physics 1 is equal to reg dot in place physics component, and that takes in the entity 1, and it also takes in the physics world. So we have to say the physics component. Cool. That'll take in our physics world. So p physics world. And then it takes in our physics attributes. So we can go physics attributes. Now we could just leave it like that, but we're going to actually put some attributes in. Let's go type, type is equal to rigid body type, dynamic, density, let's make it equal to 100. Friction, 0.5. Restitution, we'll just leave that for now. Actually, we'll put that in. Restitution, and we'll just have that at 0 for now. The radius. And that's going to be equal to our circle 1 dot radius times pixels 2 meters. Gravity scale, let's make that 5. Position, that's going to be equal to our transform 1 dot position. Scale is equal to transform 1 dot scale. And this one is going to be a circle. True. And it's not going to have a fixed rotation. Cool. And that should be our physics component. And then we're going to have to initialize it. So physics 1 dot init. And we need to take in the world width and height. And that's just 640, 480. And let's add a sprite. So auto reference sprite is equal to reg replace sprite component. And it takes in the entity 1. Sprite component. Now the size of this sprite is, go here, 128 by 128, I believe. Yeah, 128 by 128. So we'll say width is equal to 128.f. I just need the height, 128.f. Start x is equal to 0. Start y equal to 0. And that's a y, sorry. And the texture name is soccer ball. Cool. All right, so that should be created. Let's just run this to see how many bugs we got to fix. Awesome, no bugs. Cool, that's great. So first thing I actually want to do is open up our main.lua and just get rid of everything that's in there. So scripts, main.lua, and all this stuff here, we can just get rid of it. I don't want anything in the Lua right now because we're not using it. Okay, so there were no errors. Let's go back to our application and we need to update our physics system. So right here, right after the scripting update, let's get the physics world. So auto reference p physics world. Physics world is equal to mp registry get context Scion physics world. And then we're going to want to update our step. So we can just go p physics world step. And we're just going to want to say 1.f divided by 60.f. Then 10 for the velocity iterations. And 8 for the positional iterations. And then we're going to want to get the physics system. So we go auto reference p physics system is equal to mp registry get context std shared pointer of the Scion 4 systems physics system. And then we're going to want to update that p physics system, update, and that takes in the registry. Cool, that should work. We should see something. Maybe not, but we'll see. All right, so we have no errors, but I'm not seeing anything on the screen. Render system. Ah, yes. So we're not seeing anything because we didn't set our UVs for our sprite. So sprite generate UVs. At least I believe this is why. And we're just going to put 128 and 128. Let's see if that works. Still don't see something. That's why. Minus 33,000. Interesting. Let's go to our physics system. It's got to be in here. So yeah, so it's putting the body there. So it's got to be in my component. Must have did something wrong here. Yeah, so that's the issue right here. This should be pixels to meters. Pixels to meters. All right, let's try running that again. There our ball goes. All right. If you didn't see that, the ball just dropped. There we go. Cool. So it looks like our physics is working. So let's quickly add in one more body so we can make sure that the ball stops. Okay. Yeah, so the fix for that was in the physics component. This was supposed to be pixels to meters. I had it as meters to pixels. So let's go back to the application and up here and create another body. This one won't need a sprite. We'll just add in like a floor. And we'll just copy all of this. Go down here. Let's just test stuff here. And we'll call this entity2, transform to, let's put this one at, start it at 0. And bring it down to like 400. And this one will have a box collider. And a box collider component. Change this to entity2. This needs to be entity2 as well. Problem with copy and paste, guys. And then we'll just put the width and have that to 480. And then the height, this can just be 48. That's good. And then physics 2. Physics world, change this to static. And it won't have a radius. Position will be position 2. Gravity scale, let's make this a 0. Density, make it 1,000. Scale 2. and not a circle. So we'll just change this to the box shape. Fixed rotation can stay. This here is called box size is equal to GLM vec2 box collider dot width box collider dot height. That looks pretty good. And physics 2 initialize. I think that should work for us. You won't see it, but the ball should stop and land on the box that we created. Awesome, stopped right there. And because it has no restitution, it didn't move at all. So let's add in a little bit of restitution for fun. Put the restitution for the box to 0.2. And let's put the restitution here, instead of it being 0, let's put it to 0.9. It should bounce. Awesome. So there we go. That's the start of our physics system that we got going on. In the next videos, we'll continue on with this. However, I do have 2 small challenges for you guys. Okay, one is in the physics component, create the wrappers for this. Just the beginning of a wrapper for the Lua bindings, okay? So we don't want to do any of this stuff here in the application. We don't want to have to do any of this. We want to be able to take all of this out and add the physics component in the Lua rather than hard coding it in the C++. That's one little challenge I have. And one more challenge would be if we look at our thing here, you can't see the colliders, right? Try to make a system where you're rendering the colliders, okay? So you're gonna have to have 2 different types of rendering. You're gonna have use your circle batch render and your regular rect or quad batch rendering, okay? So let's go to our rendering here into our core. So we have our rect batch, and you're also gonna use the circle batch because you're gonna have circles in there as well. Try your best, see what you can do. See if you can create it yourself, make your own where you're rendering the shapes on top of the textures or whatever that you're doing. All right, so that's it for this video. I'll go over my implementation in the next video, and then we'll continue on with the physics and Box2D. All right, take it easy.